to the boiler feed and cooling water treatment webinar this morning. Let's move to the desktop, and we will, well, I click on it right here. I didn't have to do that. And then Greg Poppe, not Pope, is with Dow Water and Process Solutions, and is the Global Application Development Specialist for Dow. And needless to say, you can see as you get along here, he's done some work in China and things as part of that, because you don't these days get involved in global water and power without running into the Chinese opportunities. So until recently, he was a project manager for an interesting software tool, and he's got a degree in chemical engineering, and originally from Nebraska. And now we'll look to our cleanup hitter, Greg Poppe. The floor is yours, Greg.
Thank you, Bob, for inviting me to speak with the group today. Appreciate that. Today I'd like to focus in on the ion exchange system of makeup demineralization plant, and show how some of the evolution of different system designs over time can really help to achieve better water quality and also lower operating costs. So maybe we can go on and just look at the outline slide here. I'll start out similar to the other gentleman with kind of an overview map of the water treatment system, just kind of focusing on the makeup demin area. And then we'll kind of progressively go through these various system designs for ion exchange plants and show how each of the steps lead to more and more cost savings in the regeneration chemicals and as well as water usage. And then we'll finish up just with a final summary table that puts it all together and makes it kind of easy to compare. So let's look first here at the water treatment map. When Tom spoke to us at the beginning of the session, he had one box which said demineralizer, I think, and so basically this is all contained within that single box, and Dave's diagram, I think, broke this up into both pretreatment and makeup water, so kind of how it compares to their systems. But I like to look at the makeup demin process in three different steps. You've got the pretreatment, which could even have even more basic units ops before this, but picking up here with the ultrafiltration or the multimedia or so forth, as Dave said, you need good water quality going into the roughing step to make it even better. And so the roughing step, we have to admit, over time, the reverse osmosis technology has really grown very rapidly in comparison to ion exchange, and that's great. But for processes where you have a relatively low total dissolved solids level, or maybe there's an extremely large desire to have the highest recovery possible, there's still a very good competitive argument for ion exchange in those systems, and that's really where we're going to focus on today. And then just to complete the map out, as you heard some references earlier, there's going to be, especially in the high pressure boilers, a need for the polishing units, either ion exchange mixed bed polisher or an EDI, often fed by some type of degasification or ultraviolet unit before that. So let's focus in on the ion exchange for the rest of this talk. And I'll start out with the original and most simple and most basic design, which is what we call the CoFlow Regeneration. It's called CoFlow Regeneration because both the service cycle, the loading arrow here, and the regeneration is performed in the same direction of flow from top to bottom of the vessel. And these kinds of systems always have a considerable volume of freeboard above the resin, maybe 50 to 100% of the resin's bed volume would be above it, which allows for a nice amount of space to do backwash following every service cycle. The vessel design is quite simple. Usually there's just some kind of splash plate or something that helps to, jet breaker at the top that helps to distribute the water. And then there's a collector plate at the bottom. It could be either a plate and nozzle, or maybe it's some type of header lateral system. So this system has a couple advantages. It's very insensitive to suspended solids, because any solids which might collect at the top of the bed during the service cycle is going to be backwashed off at the end of the cycle. And compared to some of the other systems, it's going to be less expensive, just because there's not a lot of bells and whistles in here. But the disadvantage of it is that it consumes a large amount of chemicals during regeneration. And even then, if you kind of look at the 5 columns on the right there, under the exhaustion title, you can use a large amount of chemicals, and at a certain point, it still becomes diminishing returns. Actually, I meant to focus you on the regeneration side first. Use a large amount of chemicals to try to regenerate, and at a certain point, there's a diminishing returns, and in the end, there'll still be a heel of exhausted resin towards the bottom of the vessel. And so then, during exhaustion as well, there's not a lot of uniformity in the way that the flow patterns work, and so you'll see breakthrough earlier, which really compromises on your water quality. So just kind of using this as a benchmark, going back to the earliest days of ion exchange, you can see in the little yellow box towards the top that you could use up to 200 to 400% regeneration chemicals on a stoichiometric basis compared to what the ions on the resin bed might be. And as we look forward, you're going to see that can be improved upon greatly with some of the other system designs. And then both the conductivity and silica removal will be better as well. So let's move on, and I'd like to just explain a little bit more why it's difficult to get good chemical efficiency off of this kind of system. Different ions have a different level of selectivity towards the ion exchange resin, and the industry kind of considers hydrogen as the nominal benchmark of selectivity equal to 1. And then you look at other ions, just some typical ones here like sodium and magnesium and calcium, each have a progressively higher affinity towards the resin. And so looking at the little diagram in the lower left of the slide, what happens during service is you end up seeing a chromatographic layering of the way these ions deposit onto the resin. Calcium, being the most attracted to the resin, essentially will displace any other kind of ion that is already there. And so by the end of the cycle, calcium occupies most of the resin at the upper layer of the bed, and sodium is progressively pushed towards the bottom of the bed, and then magnesium is going to fall somewhere in between. Well, when you then come to regenerate this, it's challenging. I mean, there's going to be a backwash before this that mixes this up somewhat, but that certainly isn't complete, and you'll still have calcium in some ways at the top of the bed. This is the component that is most difficult for the acid regenerant to remove, and yet it has to be pushed all the way through the length of the entire bed. And is just an example why at a certain point it becomes economically unfeasible to really apply more and more regenerant to try to do that. So it becomes pretty costly. If we go to the next slide, we see how reverse flow regeneration can be a very, very nice step forward in helping to reduce the chemical costs. So in reverse flow regeneration, we still have loading or service in the downward direction, but now regeneration occurs in the opposite direction, from bottom of the vessel to the top of the vessel. And you can see then on the diagram toward the bottom the advantage that this offers, because you end up getting the acid to contact the bottom of the bed, which in the service cycle is the exit point, So you create a very nice polishing zone where acid is always in contact with that amount of resin that does the polishing. And then the other nice thing about it is the acid is in first contact with sodium. Sodium is has less affinity than, say, calcium and magnesium, so it's easier to remove. But then sodium is moving upward in the bed and helps to remove the magnesium better than hydrogen alone could. And in the top of the bed, then, both sodium and magnesium are helping to coax the calcium away from the resin sites. So you have a very nice cooperation of the different ions helping to remove the ones above them. And as you can see in the upper right-hand corner of the box, the regeneration ratio could save you as much as twice the amount of chemicals through this type of operation. Now, the trade-off is that the system design is going to be a little bit more complex. You can see in the diagram there that there's an additional dark line in the middle of the vessel which represents a collection lateral for the regenerant. So that's an additional cost to the overall system. Also, it's very important that the bed remain in the layered state that it is at the end of the service cycle, with sodium at the bottom and calcium at the top. And so in order to preserve that, there is either a water block or an air block that comes down through the bottom or through the top of the vessel, which essentially holds the bed down as the regenerant chemicals flow up. And so there's some additional valving and control involved with that. But overall then, as you can see, everything is improved fairly dramatically from the standpoint of conductivity to silica removal, and finally the yield. And again, there will be a summary table at the end that puts that all together.